Good morning. It's 11 a.m. here in Philadelphia, and welcome to the EMC Live 2016 Test and Design Bootcamp. I'm Graham Kilshaw with Interference Technology Magazine, and we are the creators of EMC Live. Today's event is a special one-day event focused on pre-compliance and compliance testing and designing for EMC. With me again today, we have Ken Wyatt, the Senior Technical Editor for Interference Technology. Good morning again, Ken.
Good morning, Graham.
And Ken will be hosting your questions and answers at the end of the upcoming presentation. The next presentation is our first technical presentation of the day, and it's brought to you by Rohde and Schwarz, who are the exclusive sponsors of today's boot camp. So our sincere thanks to Rohde and Schwarz for making today's event possible for everyone. The title of the presentation is The Value of Preselection in EMC Measurements. And the speaker this morning from Rohde and Schwarz is Bill Wangard, coming to us from Chicago. Good morning, Bill.
Good morning.
Bill is the product manager for EMI receivers, EMC software, and amplifiers. And we'll begin his presentation very shortly. But first, a few tips for you, our audience members. First of all of today's presentations and slides will be recorded, and they will be available to you within 2 days or less to download. You'll automatically receive an email from us when those presentations are ready, so no need to contact us. We will contact you. You can submit your questions at any time during the course of the presentation, and Ken Wyatt and Bill will be there to answer as many of them as possible when we get to the end of the presentation. Last of all, at the bottom of your screen, if at any time you would like to take a look at what's happening on the Rohde and Schwarz website, you can click the link button, and that will take you there directly. And with that, I'd like to hand over to Bill Wangard to begin. Bill, over to you.
All right, thank you very much. So I'm going to begin the presentation with the videos. Very often when discussing the topic of pre-selection, I'll get a customer that says, hey, I've been in the industry for 10 years and I've never seen it make a difference. So a lot of this presentation is going to be covering pre-selection, why it's there, what about it, and convincing people that yes, there is something to the pre-selection and that there's a reason for it. So with that, I'm just going to start this video and I'll explain it as it's playing. So here we have a receiver inspection analyzer mode, and in that mode, in this piece of equipment, you have the ability to turn the pre-selector on and off. So right now, the pre-selector is off. There's no overloading indication, and you're measuring frequency versus amplitude as you would in a normal measurement. But there's no indication from this measurement that there's anything wrong. So now what we're going to do is copy over this trace, what would be your data in your system, into another trace, and then we're going to turn the pre-selector on and rerun the measurement with the exact same input to the receiver, and I'll discuss that at the end of the presentation and go through what the stimulus was. But basically, it was just a CISPR pulse generator. So now again, we have swept through a normal response without a pre-selector. Turning the pre-selector on right now, and you're going to rerun the exact same measurement. And here it is. A completely different response with no overload indication or nothing to indicate that there's anything different about the measurement. And the first question is, okay, with the pre-selector on and pre-selector off, do you get a higher or a lower value result? And the answer is, it depends on what type of frequency or what frequency that you're measuring at. So with that, I want to start the presentation showing you that you will get different results depending on what type of signal you're trying to measure. And with that, we'll go into the agenda. So the outline today is spectrum analyzers versus EMI receivers, a very brief discussion on the difference in the architecture. And then we're going to talk about pre-selection of standards, the MIL-STD461 and CISPR 16-1-1. And we'll cover the time frequency characteristics of a pulse and the pulse requirements of CISPR 16-1-1. We're not going to get very technical in depth, but just enough to let you know that the pre-selection matters. It's in the standards, and it wouldn't be in the standards if it didn't matter to the everyday engineer trying to make these types of measurements. So the other thing I get asked about is what is the difference between pre-selection in a spectrum analyzer versus pre-selection in a receiver. So we're going to cover that pretty thoroughly. And then we'll come back to the video that we just saw and explain what the input stimulus was and give a little bit more background to that. So with that, jumping in, spectrum analyzer versus EMI test receiver. The application and purpose drives the difference in architectures of the two. So spectrum analyzer typically, and I'm referring to more of a traditional swept spectrum analyzer, makes accurate measurements of somewhat typically known signals for proper characterization. A receiver is meant to characterize unknown signals in a repeatable manner per a specification in a standard. And that difference in purpose is going to drive differences in architecture that we're about to see, but some of the main ones are the architecture of frequency swept versus frequency stepped versus time domain scan, types of detectors, and of course today's topic is pre-selection. Okay, so looking at the main architectural differences, you have an RF input for the signal that you're trying to measure or characterize. It comes into the attenuator. And now you have this preamplifier or pre-selector, which is one of the main differences, again, between receivers and spectrum analyzers. Other differences that we're not really going to touch on very much are the detector types, AGC, which is automatic gain control in a receiver to eliminate overloading and increase dynamic range, the IF filtering, and then also that local oscillator, which we're going to cover in one slide because it also talks to another point in the presentation about reducing the opportunity for invalid results. And that's a lot of what the pre-selector does. It reduces the opportunity for invalid results. Okay, so a spectrum analyzer, a traditional swept, it continuously sweeps across the frequency range. And you have to calculate, hey, what's the measurement time at each frequency? So you have to know the sweep time divided by the number of sweep points. Now, what's the spacing and step size between each measurement point? Well, that's the span divided by the sweep points number -1. You have to calculate certain things to make sure that your measurements are correct and that you don't have any errors in the way that you characterize it per the standard. Now, if you go to a receiver, it's what I will refer to as frequency stepped. So you are stepping to a frequency, you are waiting for the LO to settle, you're dwelling for the measurement time, making the measurement, and now you step to the next frequency and repeat. So the nice thing about this is you directly set that measurement time. You don't have to calculate the measurement time from the sweep time divided by the number of points. You directly set the frequency step size so that there is no calculation that can be made inaccurately. And what it does is it removes most of the opportunities for user configuration error via user interface designed specifically for EMI or EMC measurements. So part of that architecture is specifically designed to make EMC measurements, removing that opportunity for error. So pre-selection, what is it? From a technical definition, pre-selection is any filtering before that first mixer to pre-select the frequencies of measurement and exclude other frequencies. So you are pre-selecting what you want to look at. So a spectrum analyzer, you can say it has pre-selection because it does, but the purpose of the pre-selection is improved signal measurement fidelity via image rejection or harmonic rejection. Now the purpose in a receiver is to eliminate overload and increase the dynamic range to make the measurement, quote-unquote, measurement apparatus comply with the standards, specifically CISPR 16-1-1, and we're going to see what that means here in a moment. So with that, now we're going to cover what pre-selection is in the standards or how the standards reference pre-selection. Okay, CISPR 16-1-1 is the standard which puts specifications on the quote-unquote measuring apparatus. And in there it says, be it a spectrum analyzer, a test receiver, an FFT analyzer, it uses a black box approach in that it doesn't care how you do it, but you must meet these specific measurement accuracies. So the MIL standard community say, okay, great, but I don't do commercial standards. I do MIL standard 461. But in reality, MIL standard 461, so our A&D folks, they indirectly reference CISPR 16-1-1 requirements via ANSI C63.2. And I don't expect anyone to remember all these standards, but I want to drive the point home that yes, pre-selection is specifically called out in the standards, and that's why I'm going to spend about just 5 minutes just going over this real quickly. Okay, CISPR 16-1-1 has requirements on the ability of the measuring apparatus to properly measure pulses. Therefore, the pulse handling requirements translate into dynamic range and pre-selection architectural requirements on the said measuring apparatus, be it your spectrum analyzer or receiver. So it's one thing to say that, but let's just quickly go through and look at the standards as they are. So this is a copy of MIL Standard 461. And what does it do? It references ANSI, ANSI C63.2. Standard for electromagnetic noise and field strength instrumentation. So what does ANSI do? Here's ANSI, and it references CISPR 16-1-1, which is radio disturbance and immunity measuring apparatus and methods. Okay, so CISPR 16-1-1, what is that? So CISPR 16 is a specification for radio disturbance and immunity measuring apparatus. What is 16-1? It's 5 parts covering the measurement instrumentation specifications. So now if you go into 16-1, here's the 5 parts, with the part 1 being the measuring apparatus. So that's where CISPR 16-1-1 comes from. And the family of CISPR product standards all reference CISPR 16-1-1. And even the MIL Standard 461 group indirectly references CISPR 16-1-1. So now that we've shown how both the A&D and commercial communities reference the standard, what is it about the standard that's so important? So first, we're going to cover the time and frequency domain characteristics of a pulse. So here you have a time domain pulse function, repeated series of pulses, and how that looks in the frequency domain. As you can see here, the shorter the pulse width or the pulse duration, that sets the inverse of the null in the spectrum. So the shorter the pulse width, the wider it's out in the spectrum. And this is just a traditional sync function for a single pulse. So this is the time-frequency duality of a pulse, and we'll see why that's so important coming up. Okay, so here is CISPR 16-1-1. Here's a table of contents. Section 4, quasi-peak measuring receivers for the frequency range of 9 kilohertz to 1 gigahertz. And what is section 4.4? It's the response to pulses. And now for the MIL standard folks, you say, I don't care about the quasi-peak, I care about the peak. Well, section 5 is measuring receivers with peak detector for the frequency range of 9 kilohertz to 18 gigahertz. And section 5.5 is that response to pulses. And for completeness, the average detector and RMS average detector are also covered in sections 6 and 7. So now that we see that CISPR does have this requirements on your ability to handle pulses or the response to pulses, what is that? So here is 4.4.1, and we're not going to go through the details, but basically we just want to show that across the frequency ranges, in different frequency ranges, you have this input stimulus, which is the energy in the pulse, the spectrum of the pulse, which in the frequency domain needs to be constant, a constant spectral density, and then that pulse repetition rate in this column. Okay, so here's a very important paragraph, and what it's going to say, for spectrum analyzers without pre-selection, the requirements in that table for pulse repetition frequencies less than 20 hertz are not applicable. The use of instruments for compliance testing is conditional. So this is telling you that the standards realize you have a need for pre-selection in order to make measurements with the confidence that you are not getting invalid results. Further on, it says, if spectrum analyzers are used for the measurements, the user shall verify and document the equipment under test does not emit broadband signals of pulse repetition frequency 20 hertz or below. I'm not going to get into the technical details of this too much, other than let you know that it's there. And then the final thing here is the determination of the suitability of a spectrum analyzer for testing shall be made by this procedure in Annex B of CISPR 16-2-1. So what does that say? What's the first consideration in that annex? First one is overload. Most spectrum analyzers have no RF pre-selection in the frequency range. So what is the CISPR saying? It said if you have a measuring apparatus without pre-selection, you have to do these certain things to make sure that you are fully compliant to the standard. So the standards body realizes the need for pre-selection to make accurate measurements, and it's covered in the A&D community and commercial community. Okay, enough of the standards. Oh, one more slide here. So this is just to give you a feel for the requirements in the table. Obviously, I'm not going to go over here, but again, it says for different repetition rates, for different frequency bands, you have to have a certain number of dB repeatability relative to another standard waveform. So they are putting requirements on that measuring apparatus to handle pulses. Okay, so that's enough of pre-selection in the standards, again driving home the point that it really matters per the standards. Now, what does pre-selection mean in a spectrum analyzer? Well, it's really for image rejection. So let's cover what image rejection is. In a spectrum analyzer or in a receiver, anything that you down-convert frequencies, so you have the input RF signal that you want to down-convert to the IF via the LO. So the frequency at the IF is the LO minus the RF, and that's what you down-convert to the IF. However, if you have an image frequency, the image frequency is about the LO, so the FIF also equals this FRF minus the LO. So it's basically the image of your desired frequency about the LO. Well, what happens is that you down-convert that energy to the IF, and now you have a signal fidelity issue. You're not worried about overloading the mixer per se, but you have this energy that is out of band that you are not trying to measure. So how do you get rid of that? You put in a pre-selector for image rejection. Is it a pre-selector because it pre-selects the frequency that you're measuring? Yes, but the purpose in a spectrum analyzer is for image rejection. It's not for overload. So let's drive that home a little bit. So here's a spectrum or a block diagram of one of our spectrum analyzers below 8 gigahertz. And if you blow it up to the input, what you're going to see is the RF comes in. Again, there's that attenuator that we covered in the block diagram in the prior slide. But right off the bat, you go through a quote-unquote pre-selector filter. But it doesn't even say pre-selector. It says image filter because the pre-selector purpose is image rejection. Now you also go through these other different filters, but they're really not important for the point of the presentation. But they're really designed there for signal integrity and harmonic performance. And then the one final thing to note here is that if you have signal frequencies under 1 gigahertz, it comes into the attenuator, goes through an image filter of an 8 gigahertz low pass, then it goes through a 1.1 gigahertz low pass filter into the ADC. So basically, you have no pre-selection when you're looking at frequencies below 1 gigahertz other than these low pass filters. And you'll see why this makes all the difference once we get to the receiver section. Now for completeness, if you have an analyzer that goes above 8 gigahertz, the analyzers will split the path. Comes in here below 8 gigahertz, it goes back to that initial board that we just saw. But if you're above 8 gigahertz, you go through what's called a YIG pre-selector or the bypass. So let's cover what that means after this slide. So here's where the below 8 gigahertz comes in. Here's where the signals above 8 gigahertz are already down converted and everything comes in to match. So YIG filter, what is that YIG filter, which is your pre-selection above 8 gigahertz? Well, YIG stands for something I can't pronounce and won't try. But it's basically a tunable bandpass filter, and it's magnetically tuned. The purpose is to provide signal integrity via image rejection, not necessarily overload protection. So what are the drawbacks? Well, it's got limited bandwidth, 30 megahertz. So if you have an application or you have something that you want to look at wider than 30 megahertz spectrum, you have a bypass. Now you've bypassed it, so now you literally have no pre-selection. And to be complete, pre-selection above 8 gigahertz isn't nearly as important as it is below 1 gigahertz, and you'll see that in the pre-selector architecture when we get into the receivers. Okay, so that's, again, the summary of pre-selection in a spectrum analyzer. The purpose is image rejection. Now let's go to pre-selection in a receiver and show how it's very different. Purpose of pre-selection in a receiver, again, it's not image rejection or improved harmonic performance. Pre-selection protects that front-end mixer and it helps eliminate mixer compression, which changes the gain and gives you invalid results. So there's two main situations where pre-selection is required. So the first is that you have a whole bunch of spectral content across all frequencies, and that all passes through to the mixer because nothing is pre-selected. And that summation of all that energy from all these different signals can overload the mixer, reducing the dynamic range and giving invalid results. And I think this is the situation that most people are familiar with. The second situation that the majority of the community is not as familiar with is what we covered up front. It's that single short duration pulse input resulting in a very wide spectral bandwidth, and that's the content, spectral content at the mixer. And that's what the standards, specifically CISPR 16-1-1, puts requirements on the receiver or measuring apparatus. So let's look at the two. So the first one, again, I think most people are more familiar with this, is that you are trying to look at this little red signal in the presence of all these larger blue signals. And those larger blue signals can overload that mixer. So you pre-select certain spectral content, essentially filtering out all this energy at the other frequencies, other signals, and now you have reduced compression on the mixer. So now we've come to what could be arguably the most important slide in the presentation, which is showing the effects of the pre-selection in a receiver. So here you have that single pulse in the time domain. It's very high amplitude and very short in duration. So what does that look like in the frequency domain? Again, the shorter the pulse in the time domain, the wider that lobe or that null in the frequency domain. Now going back to Signals and Systems 101, so you can represent a signal in the time domain and you can represent the signal in the frequency domain. And you can calculate the energy in the time domain and the energy in the frequency domain. And it should be intuitive that those energies should be equal, because whether you represent it in one domain or the other, you have to calculate the energy and it should be equal. So what does a pre-selector do? It's going to pre-select out frequencies that you want to look at and eliminate all the frequencies that you don't. So what does that do? That filters out energy in the frequency representation. Well, if you filter out energy in the frequency representation of the signal, then it also is going to correspond to the time domain of the signal. And that's what happens. So here's your original pulse. It goes through the pre-selector. Not only does the amplitude significantly decrease, which stops you from overloading the mixer and giving you an opportunity for invalid results, but it also draws out that signal in the time domain. And we're going to see why that's important in a few slides here. So again, high energy in the time domain, pre-selection filtered out, and it affects the time domain, and now you're less likely to overload. So let's look at what does pre-selection look like in a receiver. And every receiver is going to have its own pre-selector because it's an architectural lineup that takes into account all of the components. So every fully compliant or non-compliant receiver with pre-selection is going to have their own type of switching. But here what you see is that you have several fixed bandpass filters covering 150 kilohertz to 1 gigahertz. So remember back in the spectrum analyzer, if you had a signal below 1 gigahertz, the only pre-selection was this 1.1 gigahertz low-pass filter. Here in a receiver, in this case it's the ESR from Rohde and Schwarz, you have a bandpass from 80 meg to 130 meg, from 130 meg to 180 meg, from 180 meg to 230 meg. These filters aren't put in here for fun. They cost money. But these filters are put in for the necessity of complying with the CISPR 16-1-1 requirements on the ability to handle that high energy pulse. So the purpose of the pre-selection in a receiver is fundamentally different. It is aimed at being able to comply with the standard and the standard requirements for handling a pulse. Okay, so here I'm going to label it something different, not the value of pre-selection, but I'm going to say the necessity of pre-selection. So you have an RF input with a high energy short duration pulse. Now it goes through the pre-selector, and what we saw before is that it's significantly reduced in amplitude and drawn out in the time domain, and again in the resolution band of filter, but that's not as critical because the ADC is actually before the RBW. So that voltage ratio is basically the ratio of the bandwidth of the pulse to the pre-selector, and we'll see why in a couple slides that's important. But a debug note, so compression can lower the gain and increase the noise. So here is a plot of the same input signal with pre-selection and without pre-selection. The red is without pre-selection and the yellow is with pre-selection. So again, if you are overloading, do you get a higher result or a lower result? And the answer is it depends on frequency. Now the other thing to point out is that the front end is overloaded without the pre-selector, but there was no reliable overload indicator. And the reason for that is the time constant on the overload indicator. If you have a very short duration pulse, that overload indicator can't respond fast enough to let you know that it's overloading. So the spectrum analyzer is overloading, it just doesn't know that it's overloading, and it can't respond fast enough to that input signal. But now when you put in that pre-selector, you've drawn out the signal in time. So you reduce the opportunity for actually overloading by reducing the amplitude, but now you've also given the receiver or spectrum analyzer a chance to detect that it's actually overloading. And we actually saw this when we made some of these videos. So what happened is that the overload indicator would only happen when we put in the pre-selector. And basically the pre-selector enabled the receiver to realize that it was being overloaded, and then you do what standard practice is, just increase the attenuation. But the fact that that pre-selector reduces the opportunity for overload and increases the opportunity to tell you that it's being overloaded. Okay, so let's just real quick go over these block diagrams, or not block diagrams, but these diagrams of the dynamic range. So basically you have a maximum input level for 1 dB compression point, and here's the noise floor. So when you have a wide bandwidth constant spectral density, that maximum overload indicator, the signal at the mixer is a summation across all the frequencies. So that power is a summation across the spectral density of the frequencies that are hitting the mixer. So you're going to decrease the dynamic range basically by the bandwidth of the signal. So now you're going to limit that bandwidth of that constant spectral density to hit the mixer, and you're going to increase the dynamic range of the measurement by the ratio of that pre-selector to the RF. So that pre-selector increases your dynamic range. And let's just put some real-world numbers on it. If you have a 1 dB compression of 120 dB microvolts, now you have a 2 gigahertz pulse. That's actually the pulse from the standard. So you would decrease the dynamic range by the ratio of 2 gigahertz to 100 kilohertz, if that's the RBW. So you're basically decreasing the dynamic range by 86 dB. Now your overload is at 30 dB microvolts. And again, that's a spectral density. That's a 30 dB microvolts at every frequency across the bandwidth that you're looking at. Now if you band select or pre-select those frequencies to 100 megahertz, now you decrease only by 60 dB. But basically you've increased your dynamic range from this value to this value. So you've gotten 26 dB of extra dynamic range, which is suspiciously close to the requirements in the CISPR world of the quasi-peak detector. So all this comes together in a way that's a little too complicated to cover in this presentation. But again, pre-selection and receiver reduces the opportunity of overloading, and it increases the opportunity for the measurement apparatus to tell you when it is being overloaded, and it increases the dynamic range. Okay, so now let's come back to those videos. What was the input stimulus in that video? It wasn't anything crazy. It was a CISPR standard calibration pulse generator. So here's what it looks like in the time domain. You can tell the pulse repetition frequency here, I think was 200 hertz. The pulse type was a CISPR for 9 kilohertz, and for the maximum RBW that we could zoom in on this with the equipment, this is what the pulse looked like in the time domain. So it was nothing tricky. So again, here we have the video that we saw originally, and then we also have a different frequency with a different resolution bandwidth, same input signal. And what I'm going to do is run the video again, just to review what we've already done. So now that we know that it's a pulsed input, and we know that a pulsed input has somewhat of a sync function response, you can clearly see that we're not getting what looks to be like a sync function response. But again, there's no overload indicator because that pulse is so short in duration, the overload indicator can't trigger on it. Now, to be fair, you could increase the attenuation, but you wouldn't know to increase the attenuation. And if you're using measurement software, the software wouldn't know to. I'm going to copy the trace. And while the video is running here, talk about applications or where this is important. So obviously pre-selection is important anywhere that you want a high confidence in your measurements that you're not getting the wrong results via overload. If you know what you're doing with the spectrum analyzer, you can increase the attenuation, but often it could be misleading. You have to really know what you're doing. So this is very critical in pre-compliance because the whole point of pre-compliance is to give you a level of confidence that you're getting the right results. And here you see from a single input stimulus that hasn't changed a very, very different response with nothing from the equipment indicating anything is wrong. So that was a sweep from 1 gigahertz to 2 gigahertz with a resolution bandwidth of 1 megahertz. So continuing on the value of pre-selection in the pre-compliance market, again, the whole point of pre-compliance is to give you a level of confidence that once you get to the test lab or whatever your fully compliant measurement system is, that you have a real high degree of confidence that you're going to pass. And the reality is that a spectrum analyzer without pre-selection will be fine for many signals, specifically signals that aren't high power, but there's a lot of short duration, high power signals that need to be characterized, and I think traditionally have been characterized incorrectly. So if you have products that have engines with quick turn on and turn off, these are short duration, high energy signals. If you're trying to characterize those, you need to really be careful that you have the pre-selection, because otherwise what you're going to see from these two graphs at different frequency ranges is that you will get the wrong results or get invalid results. And as soon as this response is done, we'll move to the summary and take questions. And there it is. So the input is a pulsed input. So in the frequency domain, we should expect to see something like a sync function, and we do when the pre-selector is on. Okay, so wrapping up in summary, pre-selection is an often misunderstood concept, but it's very significant. It has a great deal of importance if you want to reduce the opportunity to make invalid results and increase your confidence when you go to a fully compliant testing. There are architectural differences between spectrum analyzers and receivers. Receivers are specifically designed for EMC measurements. Spectrum analyzers are not. Pre-selection in a receiver is very different than pre-selection in a spectrum analyzer. Pre-selection enables a fully compliant receiver to be fully compliant to the standards. Without pre-selection, a fully compliant receiver could not be fully compliant. And then again, one of the main themes here is that pre-selection significantly reduces the opportunity for invalid results, which is the point of pre-compliance and obviously full compliance measurements. But in a pre-compliance application, you want to do anything you can to make sure that you have a high degree of confidence in your measurements. And with that, Ken, I'll pass it to you for questions.
Well, thanks so much, Bill. Audience, this is the time to send in your questions right now, and looks like we have several coming in. Just give you a minute to do that. Okay. Well, here's one question. Kindly name a few EMI receivers in the market. I'm assuming that includes pre-selection, and I also assume that Rohde and Schwarz has a model that does that. Can you name any others that the audience might consider?
Yeah, I do work for Rohde and Schwarz, but to be honest, what I would consider is there's really two main players in the market, and that's Keysight with their MXE, and it is a good receiver. It does have pre-selection, which enables it to be fully compliant. So I would say that's the one main competitor or other player in the market for full compliant receivers. Rohde and Schwarz, we have a long history of receivers design, fully compliant receivers. We have the ESR and also the new ESW, which, sorry for the product pitch, but it was the product of the year from EMC Live in April. So players in the market, I'm not too familiar with some of the players in the pre-compliance market. I think that's really governed for spectrum analyzers. But in the full compliance market, I think the two main players are Keysight and Rohde and Schwarz.
Okay, thank you. Okay, here's a question. I think I know the answer to this one, but I'll let you answer it. Is it possible to use an oscilloscope for EMI pre-compliance? It's a little
Sure.
off the track, but maybe you could answer that.
Yeah, so
quickly.
you can use many things for pre-compliance. So pre-compliance is just meant to give you some level of confidence that once you go to that full compliance measurement, you're going to pass. So there's differences in when you would want to use an oscilloscope versus a spectrum analyzer versus a pre-compliant receiver versus a full compliance receiver. But oscilloscopes and the EMI debug definitely have their role in pre-compliance. And even internal to Rohde and Schwarz, we get a little sensitive about the terminology in terms of pre-compliance versus EMI debug. So people can say that it's pre-compliance, and in a way it is, where if you want to be a little bit more purist about what pre-compliance means, it means, to me, making an actual EMC measurement where the measuring apparatus isn't compliant to the standards, but it's an actual measurement. Now, with an oscilloscope, to make an actual field measurement on a radiated emission, you need to know the K factor of the probe, and you need to know certain things, which you don't. So I would term that more EMI debug, but it is 100% fair to label that in the category of pre-compliance. If you want to use the definition of pre-compliance as any measurement to give you some varying degree of confidence that when you go to a full compliance measurement that you'll get the right result.
Yeah, I think that's a great answer. One of my specialties is pre-compliance testing and debug, and I find oscilloscopes are very useful for things like evaluating ringing on power supplies and measuring rise times and so forth. But really, I think the tool of choice for actual pre-compliance measurements is going to be the spectrum analyzer, or better yet, the EMI receiver. Again, you do probing and so forth for debug, but pre-compliance, you're actually trying to duplicate as best as possible the actual compliance testing, usually at your own facility, to give some idea of whether you're going to pass or not. So let's move on. Let's see. Here's a question from Mario. We have recently seen receivers on the market which declare they do not have pre-selection at all, yet they say they are full CISPR 16-1-1 compliant. One of them says it is able to get a one-shot slice of over 600 megahertz. How can that be possible?
I know what you're talking about, and I don't. We're in a gray area here because there's marketing materials that every company will put out, and you have to be very, very careful to read in between the lines. And what I would recommend, if you're going to purchase a receiver, I would highly recommend that if you're going to purchase that receiver, I would like a document of conformity from the manufacturer that it complies with the standard. And that's about as deep as I want to go. I'm sure you can read between the issue.
Yeah.
And I don't want to say anything derogatory or it's a sensitive technical issue, and all I can say is request an official legal declaration of conformity from the manufacturer that they truly comply with the entire standard. And I'll leave it at that.
Okay, good answer. Richard asks, why not always use pre-selection if the data is to be considered valid or not to be misled?
So that's a great question. The answer is why you wouldn't use pre-selection is if for budgetary reasons you don't have a piece of equipment with pre-selection. There's also other cases where, for example, in our receivers, we have a spectrum analyzer mode where you can turn on and off the pre-selector. But if you know that you're not going to overload because of the type of signal that you're characterizing, you may get a little faster response without the pre-selector. That pre-selector makes you switch different filters and can slow you down. So there are cases where if you know what you're characterizing to be not a type of signal that you're concerned about overloading, turning off that pre-selector may speed up your measurement a little bit.
Okay, very good. Okay, I think, let's see, here's a question from Shafiq. Is the pre-selection more necessary for spectrum analyzers than for receivers?
That's a good question. I would say it's really, boy, I'd have to think how to answer that. Is it more necessary? I think it's equal. At the heart of a spectrum analyzer and a receiver, they basically do somewhat the same thing in terms of taking an input signal, down converting it, possible multiple times, putting it into ADC, and post-processing those samples. The difference in the architecture represents the difference in the application, which is specifically EMC measurement. So is it more important in one or the other? No, it just gives you the opportunity to make the measurement.
Well, here's a question from me. Here's a question I have, Bill. If you're making measurements in a shielded chamber where you probably won't expect to see out-of-band signals that could affect your measurement, how important is pre-selection in that kind of environment where you're just measuring the emissions from equipment?
Right, and it would depend on the emissions from that equipment. If it's a very high-powered device, are you doing it conducted or radiated? Conducted is obviously more important because you have higher energy there. So it's really a function of knowing your device and what you're testing to see if it's going to radiate anything that could be at a level that would overload the receiver or spectrum analyzer. And I do have, I do believe that a vast majority of measurements are made on devices under test that will generate signals that will not overload the spectrum analyzer. So I have full confidence that a majority of what's being characterized is correct, but I also have full 100% confidence that there is this percentage of measurements that are being made wrong. And part of it comes to the engineer having some feel for what is being emitted from the device under test.
Okay, thanks, Bill. One last question, and then we've kind of run out the clock. So this is from Gurang. is the pre-selection the same for spectrum mode of EMI receivers?
That would.
The same?
Yes. Yeah. Well, yes, it does. It does. So in the block diagram of the equipment I have, it is the same pre-selector. Yes.
All right.
In the receiver,
well, Bill,
let me just clarify that. So in spectrum analyzer mode, in a receiver, the pre-selector is the same as the receiver.
Okay.
Okay.
All right. Well, we got to wrap this up. So, Bill, thanks so much for your presentation. Very informative. Audience, if your questions were not answered, we will be answering those via email in a few days. And the next up is starting right now, 11:45 Eastern, from Amplifier Research, where they're going to be demoing multi-tone testing for radiated immunity. And so you'll want to dial in right now. Bill, thanks so much, and we'll be signing off.
Thank you. Goodbye.